All right, this is going to be an introduction to 11.1 space figures. You generally refer to them as 3D figures, three-dimensional figures. Everything we've talked about so far in this course has been either one-dimensional, so a point or a line or an angle. And now in chapters, I think 6 and 7, they start talking about, well, even the triangles we've worked in chapter 4, they become two-dimensional figures. So they're in your flat plane two-dimensional figure. There's no depth to them. They have that length and width, or left and right, forwards and backwards, or left and right, up and down. But they don't have that third dimension. Whether if we're saying our two dimensions are left and right, and then forwards and backwards, then they don't have the up and down, and that up and down would be the third dimension. So this GeoGebra here that I've developed, it's on my website. My website, if anybody is interested in, is that right there. And I created it probably, I don't know, at least 10 years ago, probably, if not longer. And I put a bunch of videos on it that I've recorded teaching classes, applets that I've designed through GeoGebra to explain ideas and concepts, and other videos that I found on YouTube that help explore the ideas that I'm trying to teach in those lessons. So if you have any interest or looking for more resources, you can obviously go there and navigate that site. It's pretty easy. The right-hand side has all my geometry stuff on it. But basically what I've done here is on this left-hand side, basically, for whatever reason, I can't open this right now. My computer won't let me open this in GeoGebra, so I have to do it on the website. But this side over here is the two-dimensionals. So you've got a left and right, and if we're talking about the X and Y axes, so X-axis left and right, Y-axis up and down. But we don't have any depth. We don't have anything coming at us or going away from us. So these are all two-dimensional shapes. What GeoGebra allows us to do is project those two-dimensional shapes into 3 dimensions. Okay, so now we're seeing, if I was looking at it like this, we're seeing the exact same thing that we see over here on the left. But now, when I look at this and adjust the plane here, we can see that we now have that third dimension. Okay, and a lot of times the third dimension is referred to as depth. But we can see that we're getting, in this case, this would be, we call this a prism. Okay, this would actually be a pentagonal prism. This is going to be this red one is a rectangular prism. This one, this yellow one, looks like cheese, is a triangular prism. And the blue one would be a cylinder. Okay, and what we can do, I can, over here on the left-hand side, I can change, let's say we want to change this red one here to a trapezoid. So now what we have over here is this trapezoidal prism. We can do all kinds of things. We can change, change the, maybe I've got an obtuse triangle there, creating then that obtuse triangular prism. And I can then grab these blue dots and I can change the depth. So here we got the 2 dimensions. Okay, so that would just be a trapezoid, 2-dimensional trapezoid. Okay, meaning that if you were another point in this gray plane, okay, all you would be familiar with is this shape. Okay, this trapezoid. If I apply depth now, I get that prism. Okay, do the same thing. I think I can pull this one up and down. I'm not sure where on the circle there, on the cylinder, where the point is to select to change the height. Same thing here. Okay, we change this. And maybe when we get to a point where we're trying to find the volume of these things, we can come back once I get this working on my other program. I might maybe have to grab a different computer to do it. We can see how the volumes change as we adjust the heights of these. So basically what happens when we do volumes, let's say that I want to look at, actually let's go back to just dealing with a square. If I want to do volumes, okay, we know the formula for the area of that square. Well, to do the volume then of this prism, okay, basically what happens is that we are going to have one more of these squares just stacked on top of it, and we find its area. And then one more stacked on top of it, find its area. And one more on top of it, and one more on top of it, and one more on top of it. Kind of like the pages of a book. If you were to find the, if we envision that the pages of the book are infinitesimally thin, okay, they're very, very, very thin, and we just consider that they have areas and not volumes, okay. In reality, the page of a book does have a volume, but if we just think about it as an area and we stack them on each other as many times as we can and keep adding their individual areas up, then the book that they create, or the rectangular prism that they create, when we add all those little individual areas up, we get what we call a volume. Okay, and that concept is actually nested inside calculus. It's one of the main fundamental concepts of calculus, is taking those areas and adding them up to get a volume. So that's just kind of introducing these three-dimensional shapes. The notes start off with just some vocabulary here. First one here is a space figure, just a synonym for a three-dimensional figure. And the idea, again, talking about three-dimensional figures, if we've got, let's see here. If we've got this as our length our width or length, doesn't matter. This then is the other, so maybe we've got length here, width there, and now we'll have our height, okay, or our depth. That's our third dimension. Obviously, three-dimensional shapes are difficult to show on two-dimensional surfaces. So what you're seeing here is a two-dimensional surface, is a three-dimensional shape shown on a two-dimensional surface. So what we end up losing we call that a projection. What we end up losing is angle measurements, because that angle right there, though in the image looks like it's obtuse, if we actually had this cube or rectangular prism in our hands, what I just traced out would actually be a right angle. So we lose that 90-degree understanding the way we visually think about it when we project a three-dimensional image onto a two-dimensional surface. The next vocabulary word is a polyhedron. Okay, poly meaning many. Okay, basically it's a 3D figure or space figure in which all surfaces are polygons. Okay, and that's pretty much what we're going to deal with in this geometry, this Euclidean geometry. It says each polygon is referred to as a face for the polyhedron. An edge is the line segment created when two faces intersect. So if we were to look at, let's say I'm looking at this front polygon here, okay, that front face, and I also then want to look at, let's say, this right face right here, then where they come together, which would be that red segment right there, that would be referred to as an edge. Okay, really every solid or dotted line in this image is an edge. It's the intersection of two faces, or essentially, if we think about it, these are planes as they extend forever. The intersection of two planes is always a line. And then the vertex is the point where three or more edges meet or converge. So there's a vertex, vertex, vertex. Same thing on all these. Okay, those are your vertices. So down here when it says, if we look at the polyhedron to the right, okay, this will eventually be referred to as a pyramid, okay, and depending on what this base is, let's say that base is a square, we will refer to this as a square pyramid. So how many vertices does it have? Okay, well, it's got 5 vertices, D, E, F, G, and then H. And their edges, the edges would be DE, be that edge right there. We're going to go all the way around, so we'd have EF. We would have this one in the back, GF. We have this one here, DG. Then we're going to go from the vertex E up to H. So EH. Do that from F to H. We'll do it from D to H. And then finish over here from G coming up to H. So those will be all your edges. The faces, just try to, I'm not going to write them all out, but each face you're going to have, we'll highlight, we have this triangle HEF as one face. We have this face here closest to us in the projection, which would be H to D to E. Then we've got this face here in the back left, which would be HGD. And then the one back here, HG to F. And then our final one is the actual, what we refer to eventually as the base of the pyramid, which would be this either rectangle here or square, depending on what they tell us that is. And that would be, and I'm just going to call it a quadrilateral now, right now, G, D, E, F. Leonhard Euler, a Swiss mathematician, discovered a relationship among the numbers of faces, vertices, and edges of any polyhedron. The result was known as Euler's formula. This guy is a pretty important mathematician, probably one of the top, I'd say 5 or 6 mathematicians of all time. Did quite a bit with natural, what we call the natural number. Sometimes in science, maybe you've heard it as Napier's constant. We call it E, and it is approximately, let's see here, see if I got my calculator. It's an irrational number like pi. It's really not a big issue right now, but might as well introduce it to you. 2.7182818285 is that number. So you'll use that quite a bit in Algebra 2, college algebra, and it's named after, or the symbol comes from his last name, Euler. There's some neat history on how that all came about, but I'll save that for you. So Euler's formula says that the number of faces plus vertices is equal to E plus 2, number of edges plus 2. Okay, so faces plus vertices equals edges plus 2. So now we can use that, and I'm going to look at this picture over here as the example. Okay, so this is a hexagon up top. What we would end up calling this is a hexagonal hexagonal prism. Sorry, and I'll teach you how we name these things later. But if we look at the faces, I'm just going to start with this one here facing us. And we've got, I'm just going to list that as the first face, and then we got this one over here, and then this one back here as number 3. And then just trace them all out. This one here as the 4th face. Then we'll do this one here as our 5th face. This one here is going to be our 6th face. Okay, so I've gone all the way around and counted how many faces are all the way around. 1, 2, 3, 4, 5, 6. And then we got the one on top, the hexagon on top, so that's 7. Hexagon on the bottom, that's 8. Okay, so we've got 8 faces. Okay, now let's count the vertices. We got 1, 2, 3, 4, 5, 6. So 6 on top, and then the mirrors down here, another 6. So we got 12 vertices. Is that equal to the edges plus 2? So if I go 1, 2, 3, 4, 5, 6, 6 edges up top, there's going to be 6 on the bottom. So there's 12 edges total there. Here's 13th edge, 14th edge, 15, 16, 17, 18 edges. And then plus 2. Does this equate? Well, that gives me 20, and that gives me 20. Okay. If you were to go into kind of like graduate level mathematics, so you go get a degree in mathematics from college, and then you take some more classes on top of that. In some of those classes on top of that, you talk about something called algebraic groups, in group theory. That's a little bit of that, just a very watered down version of that concept. But this is true. Okay, so and this is just one example of it, but it is a theorem that we could prove if we had the time. So it's asking here, okay, well, can we use that formula? Okay, we've got this polyhedron in front of us. Okay, can we use this formula just to find out the number of faces? So faces plus vertices is equal to edges plus 2. If I don't know faces, so I'll leave that as F. My vertices is 20. Edges are 30 plus 2. Well, what does F have to be in order to get 32? Well, it's got to be 12. Okay, that's just a little simple algebra there. Same thing again here. Faces plus vertices equals edges plus 2. So 20 faces plus 12 vertices is equal to E, which is what I'm looking for, plus 2. So we got 32 is equal to E plus 2. Solve for E. E would be 30. So that's kind of how you go about doing that. You'll have a couple questions in MathXL getting you to use Euler's formula. Beyond that, will you ever use that? I highly doubt it. Like to talk about cross sections. Basically, cross section is when you take a polyhedron 3D figure and you slice it very, very thinly with another plane, and the location of where the plane and the solid intersect is referred to as the cross section. So this yellow plane, you can view that as like a, I don't know, I like to think of it as like a knife, and I'm cutting through maybe this. If you guys have ever seen like, I think it's called Toblerone. I can't say it. Toblerone chocolate comes in triangular prisms. If you were to take a plane as in a knife and cut through, okay, you're going to create this triangle as the cross section. Okay, whenever you take a solid and slice, I like to think about maybe taking if you were to take a loaf of bread. Okay, you see a loaf of bread before anybody slices it, you got a solid. If you were to take a knife and slice one slice of very, very, like when I say infinitesimally, the thinnest piece of bread you could come up with, that slice of bread is referred to as a cross section. So one thing we're interested in doing is trying to figure out what would the image look like for a cross section of certain solids. If I look at this cylinder being sliced by this yellow plane here, the cross section I would get would kind of follow that blue image there. Okay, it would be a rectangle. Okay, I don't know if I still have. I don't know if I'm gonna be able to do that on here to find real nice cross sections. I don't think I can do it very easily. I'm not gonna try. If you come down here, describe the cross section here. So we've got a, if you visualize like a donut or a bagel, okay, like if I were to cut through a bagel, then what you end up with would be that two-dimensional shape right there. If you remember what we called that in one of the sections in the last chapter, called that an annulus. If I look at the cone here being intersected with a cross section here, what you're going to get is that image there, which is a triangle. Now there are, and see if I should have it here somewhere on my website as well, a very common and useful topic in college algebra is something called conic sections. I don't know if I still have the, there we go. So here, what this is showing, we see basically what we've got, these two green cones are inverted on one another, so that meaning that they touch each other at their vertex. And then we take another plane and we intersect that plane with the cones. So we see that blue plane intersecting the cones, and I've got it highlighting then where that intersection is. You see that blue line being the highlight of the intersection. And then it is demonstrated over here as a, if you look at that, okay, now this is interesting because that plane is parallel to the edge of the cone, okay, or this, we call that the slant height of the cone. When the plane is parallel to that, what we end up with is this image here, and that is a parabola. Okay. Now, as I tilt that plane, that actually is one of these. There we go. If I tilt that plane, okay, now we start to intersect the cone in a different manner, and now you can see at that intersection when the plane is not parallel to the slant height. Okay, and basically you can see over here on the right hand side the differences. So this angle here, which is half of basically the, you know, if I were to take a segment from this point straight to the center of the circle in the cone, and look at that angle, we're calling that alpha. And beta is this angle that the plane makes with that line that's going through the center of the cone. If alpha is less than beta, what we end up with here is a oval. Okay. Now, the geometric word for oval is ellipse. Okay, so we get an ellipse there. And I can slide this plane up and down as well, but I still, no matter where it intersects either cone, I'm getting that ellipse. Okay, and I can make that ellipse more drastic or less drastic. Now there, you see that the plane is parallel to the base of the cones. So now the image that I get, the cross section that I get, is a circle. Okay. Now the one that you're probably not familiar with, the image that you're not familiar with, geometrically, or I guess algebraically, you'll do this in Algebra 2. That cross section there, okay, gives me this image over here. If I were to put in, I don't know if it puts my axes in here. Okay, so this is what we refer to as a hyperbola. Okay, so we get four different things when we take a plane and cross it with a set of inverted cones. We either get a parabola, an ellipse, a hyperbola, or a circle. And those are referred to as conic conic meaning cone, conic sections. So just trying to maybe foreshadow where some of this stuff will become useful to you. Some of you have seen MRIs and CAT scans. Basically what those are, if we got a CAT scan here on the left-hand side of somebody's face or head. So here's their nose, chin, and basically what happens if you were to ever take a CAT scan, basically what it does is it creates a bunch of images that a doctor can kind of flip through and see different sections of your brain or whatever part of their body that they're interested in scanning, and they can start to see where issues may be. But each one of those images is a cross section of, in this case, obviously, of your head. So hopefully that gives you a little bit of a understanding of 3D images, also referred to as space figures. Next video, we will get into 11.2, surface area of prisms and cylinders. The handout, Precious, at the beginning, the handout that you currently have, that is going to take all of Chapter 11, so you're not going to get any more handouts. Keep that. Continue to work through it. When we get to Chapter 12, start talking about circles in a little bit more detail. There'll be a separate handout for that. I am going to open up a Chapter 10 test. You can do that at your own leisure. Basically, the moment I open it, which will probably be Monday evening, I'll open that up, and you'll have an entire week. I'll give you 7 days to complete it. I'm going to, it's not going to give you similar exercises. It's going to have one question that you can answer, but it will give you the, if I answer it wrong the first time, I'm going to get 3 total chances on that question. Now, just be careful, because some of them, if they're not coming from a pool that has the ability to give you, like if it's a multiple choice question, generally they don't give you 3 chances. It'll tell you final submission or not on the bottom right when you click the answer or click the submit button for that question. So it'll give you an opportunity that if I've missed it one time, I can reevaluate, go back through my notes, all that kind of stuff, and see if I can answer it a second time correctly. If I can't do that, then third time, hopefully you spend a little bit of time maybe asking some questions to get that answer correct. Obviously on that, I can't control, because it's going to be a take-home test. I can't control resources, so my thoughts are use anything you can. I would prefer that you don't use one another. Use your notes. I want to know what you know. I think I'm giving you enough kind of leeway with it that you're not forced or feel like you're forced to utilize somebody else's help, and that you can take the necessary steps to do well on that exam under your own powers and own efforts. As we move closer to May 2nd, and I think it's May 2nd and May 3rd. Let's see, May 2nd and May 3rd, or maybe May 3rd and May 4th. Second, no, it's the 1st and 2nd. The 1st and 2nd, those should be the 2 days for our EOC. As we get closer to that, probably this week here, the 15th, I'll start giving you some tools that you can use on your own to prepare for that test. Simultaneously still continuing through chapters 11 and 12. Hopefully by that time we're on to chapter 12. But I'm going to use some of that stuff to, there's some online assessments and stuff like that can be useful to you in preparation for that test. As always, if you have questions, don't hesitate to come see me. Reach out to me via email or talk with Mr. McCoy. Mr. McCoy is enjoying his time with you guys and really wants you guys to utilize him as a resource. So please do that.